In the last video, we saw our first example of trig substitutions, and you were probably fairly overwhelmed, like it's kind of intimidating the first time you see it. But the idea was to break it down into a three-step process, where we first get rid of the square root. Doing so isn't easy. It involves a process that's a lot like a u substitution, although we tend to use the letter theta instead, and some simplification that ends up involving the Pythagorean identity. But the advantage of doing all that is you're left with some trig expression that you're able to integrate. Sometimes integrating that trig expression will be really hard, sometimes it'll be fairly easy, and sometimes, like the last example, it'll be, somewhere in the middle. Often you'll again want to use some variant of the Pythagorean identity. When you finish part 2, you should be feeling really good. You don't have any integral symbols left. You end up with an expression that represents your answer. The only problem is the variable. Because we did a substitution in part 1, we need to substitute back in part 3. And that's not too hard to do, especially if you're comfortable with these two expressions representing the same substitution. But where things get challenging is simplifying, because even after you substitute back, your work is not done. You're typically going to be left with an inverse trig function nested inside of a trig function, which you'll be expected to simplify using a method that you may have learned in a trig class, which frankly is pretty challenging in its own right. Anyways, the point is just, it's a lot. What I want to do in this video is do another example, frankly an example that's going to work out a little bit nicer, but I want to go through it much more quickly. And even though it's a different example than we did in the previous video, I want to really emphasize the fact that there's a lot of commonalities between what we'll be doing when we try to integrate x times the square root of 25 minus x squared, and what we did when we were trying to integrate the square root of 9 minus x squared divided by x squared. The first comment that I'll make more concrete at the end of the video is the way you would know that this is a trig substitution question is the fact that we have a radical with these two different terms underneath the radical. 9 minus x squared in the previous video, 25 minus x squared in this video. There's more to this integrand than just the radical, namely there's this extra x out here, but it's the radical part of this expression that'll be your hint that you want to use a trig substitution. One more thing before we finally integrate this thing with a trig substitution. I want to make the point that we don't need a trig substitution for this specific integral. This specific integral can be integrated using a much easier method. Because the derivative of 25 minus x squared is negative 2x, and we have this x outside of the radical, a u substitution will actually work out really nicely here and be a much easier way to get the right answer. However, even though there's an easier way to get the right answer, I think it'll be instructive to see how we can come up with the exact same answer using this new method of trig substitutions. So first, integrating this really quickly using a u substitution. If I were going to use a u substitution here, what I would do is I would let u be equal to 25 minus x squared. With that choice, du is equal to negative 2x dx. In other words, negative 1/2 du is equal to x dx. And with these substitutions, I can rewrite this integral as, the x dx would change into a negative 1/2 du. So there's the du part, and the negative 1/2 is just a constant. So I can pull it out in front of the integral symbol. And then I got the square root of 25 minus x squared. However, 25 minus x squared is just u. So I got the square root of u, in other words, u to the 1/2 power. With these substitutions, the integration is fairly straightforward. I leave the negative 1/2 completely alone, and then I look at this and think about the power rule. If I add 1 to the exponent, it becomes u to the 3/2 power. But I'm not done, because the derivative of u to the 3/2 power is not u to the 1/2 power. It would be 3/2 u to the 3/2 power. I don't want that extra 3/2, so I need to put a 2/3 out in front. Technically, I tack on a plus c, and I'm done with my integration. However, even though I'm done with the integration, I shouldn't leave my answer here, because u is something that I created in the problem. The original problem had x as the variable, so I need to substitute back. I guess I might as well simplify negative 1/2 times 2/3 is negative 1/3 if I cancel out this 2 and this 2. And then instead of u to the 3/2 power, I could write 25 minus x squared raised up to the 3/2 power plus c and be done. Not too bad of a problem. Somewhere between a beginner and intermediate level u substitution problem. But again, we're not trying to learn u substitutions here. We're trying to learn trig substitutions. So let's see if we can get this exact same answer a much more challenging way. I'm starting out with the integral of x times the square root of 25 minus x squared dx. The big problem with this integrand is the fact that I have two terms underneath the radical. So my goal is to get rid of this square root sign. That's what I do in part 1. How am I going to get rid of this square root sign? By doing my trig substitution. Last time when we had 9 minus x squared in the integrand, what we ended up choosing for x is 3 sine of theta. I guess technically we chose theta was equal to the arc sine of x over 3, and then solve this equation for x to get x equals sine of 3 theta. If you can get to the point where you can look at this and recognize that the exact same equation, that's really good. Okay, so that was our choice when we had 9 minus x squared underneath the radical. So what would be a logical choice if we had 25 minus x squared under the radical? Well, really, it's the exact same, except the 9 changes into a 25. So if you just had to guess blindly, you might be like, well, 3 is the square root of 9, so maybe I would choose the square root of 25. Maybe I should choose 5 times sine of theta for my value of x. Or more technically, theta would be the arc sine of x over 5, which is equivalent to x is equal to 5 sine of theta. And in fact, that's exactly what you're going to do. We're going to let theta be equal to the arc sine of x over 5, and then rather than figure out d theta right now, because taking the derivative of arc sine is so ugly, we're going to solve this equation for x. Take the sine of both sides, we get sine of theta equals x over 5, and then multiply both sides by 5, and we get x is equal to 5 sine of theta. Again, most books start you out right here and say this is the substitution. I just think it can be a little bit confusing. I think it feels more like a u substitution if we decide what theta should be equal to in terms of x, as opposed to figuring out what x should be equal to in terms of theta. We start here, we solve for x, we take the derivative, we got dx is equal to 5 cosine of theta d theta. Cool, now that we know x and dx, we can rewrite this expression as 5 sine of theta times the square root of 25 minus 5 times the sine of theta squared. That takes care of all the x's. Now we take care of the dx. dx is 5 cosine of theta d theta. So I multiply this entire thing by 5 cosine theta d theta. It looks like we've made life a lot worse. This looks like a much more challenging integral to evaluate, but it'll turn out it won't be. Let's see, first comment, 5 sine of theta times 5 cosine of theta is 25 times sine of theta times cosine of theta. So I can take the 25 and bring it out in front of the integral, and then I have a sine of theta sticking around and a cosine of theta sticking around. But then I still have this stuff underneath the radical. If I get rid of the parentheses, 5 sine of theta squared is the same as 25 sine squared theta. So what I end up with underneath the radical looks a lot like what I ended up with underneath the radical last time. Remember we had 9 minus 9 sine squared theta, and I made the comment that this constant was the exact same as this coefficient, so I could factor that 9 out and be left with 1 minus sine squared and apply my Pythagorean identity. That exact same thing is happening here. And it's not a coincidence. It happens because of what we chose for our value of theta. Anytime we choose theta to be the arc sine of x over some constant, that constant will be chosen really carefully so that this step works out. Anyways, underneath the radical here, I factor out a 25 from both terms. That leaves me with 1 minus sine squared theta in the parentheses. Now I use my Pythagorean identity, and I change 1 minus sine squared theta into cosine squared theta. That's the big step, right? Remember, the problem was the radical. I couldn't get rid of the radical because I had 2 terms. But by doing this factoring and using my Pythagorean identity, I've changed it so I only have 1 term underneath the radical, which is awesome because now I'll be able to cancel out this square root. The square root of 25 cosine squared theta is equal to 5 cosine of theta. Technically, it's equal to the absolute value of 5 times cosine of theta. But as I mentioned before, we don't have to worry about that technicality. Clean this up a little bit by pulling the 5 out in front and rewriting cosine of theta times cosine of theta as cosine squared theta. I get 125 times the integral of sine of theta cosine squared theta d theta. At this stage, I'm done with part 1. Technically, part 1 just says get rid of the square root, so I guess you could argue we were done with part 1 line earlier, but I like to clean things up a little bit when I can before moving on to the next part. Part 1 is done, now we try to integrate. Interestingly, the way we're going to integrate here will be one of the many techniques we learn in the next section, but this specific example of it is not a very complicated technique, and I think I can just show it to you right now. The idea when you're integrating this is recognizing that the derivative of cosine is almost equal to sine. So if we do a u substitution here, where u is equal to cosine, the du will take care of the sine, and we'll end up with an integral that's really easy to evaluate. What I'm saying is for part 2, I'm going to do a u substitution where I let u be equal to cosine of theta, in which case du is equal to negative sine of theta d theta. In other words, sine of theta d theta is equal to -1 times du. Sure. With these substitutions, this expression becomes 125 times the integral of, instead of sine of theta d theta, I'll write -1 du. There's the -1, there's the du. And then instead of cosine squared theta, because cosine of theta is equal to u, I can just write u squared. The integral of -1 u squared, that's really easy. I could pull the -1 out in front, and then I would just have to take the antiderivative of u squared, which we know to be equal to 1/3 u cubed, tack on a plus c. You could save this next step that I'm going to show you for part 3, but I think it kind of makes more sense to do in part 2, because really part 2 started with 125 times the integral of sine of theta cosine squared theta d theta. And I'd argue that -125 times 1/3 u cubed plus c isn't really done integrating this expression, because down here our variable is u, whereas up here our variable was theta. So maybe I should take it one step further. Maybe I should call it -125 over 3 times, and then instead of writing u, since u is just equal to cosine of theta, I could write cosine cubed theta. I think now we're done with part 2. Our third and final part, part 3, is to change variables back. And to be clear here, what I mean is from theta back to x. And this specific example got a little bit complicated because we also changed variables in our integration step. To change our variables from thetas back to x's, what we got to do is remember what substitution we did to change from x's to thetas. We said theta was arc sine of x over 5, which is equivalent to x being equal to 5 sine of theta. So we take this expression and we change all the thetas into arc sine of x over 5. That gives us -125 over 3 times the cosine of the arc sine of x over 5, all cubed. Not a horrible idea to remember to tack on the plus c. We don't have any integral symbols. Our variables are x's. You're probably feeling pretty good if you get this far. And frankly, I'd be pretty happy with you if you were able to get this far. This is a really challenging method, but no book will ever leave their answer this way. Really, what we should do at this step is simplify, because what we have is an inverse trig function nested inside of a trig function, and you can always simplify when you're in that instance. So this is the and simplify part of part 3. We're going to simplify the cosine of the arc sine of x over 5. The way we do that is with this same substitution. We let theta be equal to the arc sine of x over 5. Same thing we have written over here. If theta is equal to the arc sine of x over 5, then the sine of theta is equal to x over 5, and that allows us to draw this pretty right triangle. Throw theta down here, and we know because of SOHCAHTOA, the sine of theta must be equal to the length opposite that angle divided by the length of the hypotenuse. So these two sides are in the ratio x to 5. If we have two sides of a right triangle, really we know all three of them. Maybe I'll call this third side a. We can say a squared plus x squared is equal to 25, because a squared plus b squared always equals c squared. And if we solve this equation for a, we get a squared is equal to 25 minus x squared. So a is equal to the square root of 25 minus x squared. Technically a plus or minus, but just like you didn't have to worry about that absolute value symbol earlier, you don't have to worry about the plus or minus. Now that we have all three sides of this right triangle drawn, we're able to simplify the cosine of the arc sine of x over 5. How? Well, we know the arc sine of x over 5 is just this angle theta. So when we're simplifying, really what we're trying to simplify is the cosine of theta. And we can simplify the cosine of theta by staring at this picture. Cosine is always adjacent over hypotenuse. So in this picture, we see that the cosine of theta is the square root of 25 minus x squared divided by 5. So that's my answer. No, that's this expression simplified. Remember, this is the answer over here in purple. So what we want to do is replace the cosine of the arc sine of x over 5 with what we found that to be equal to. So we still have this negative 125 over 3 out in front, and then we have something cubed plus c. That something, cosine of arc sine of x over 5, can be written as the square root of 25 minus x squared over 5. I think this would be a perfectly acceptable answer. However, I want the answer down here to look like the answer looked when we did a u substitution to start this video. So I'm going to simplify this just a little bit more. I'll leave the negative 125 over 3 alone for a minute. I'll think about the square root of 25 minus x squared as 25 minus x squared raised up to the 1/2 power. And when I have something raised up to the 1/2 power cubed, that's the same as raising it up to the 3/2 power. 1/2 times 3 gives me the 3/2. So when I cube the top of this fraction, I get this expression. When I cube the bottom of the fraction, 5 cubed is equal to 125. So I get this 125. Oh, how convenient. These 125s cancel out, and I get negative 1/3 times 25 minus x squared raised up to the 3/2 power. I should have put a plus c here, and I should put a plus c here, and this will be my final answer, which I really hope matches up with what we came up with when we did this with the u substitution. Yeah, sure enough, it does. That's awesome. And yeah, in this specific instance, the u substitution was much easier to get the right answer. But our purpose wasn't to get the right answer. Our purpose was to practice these trig substitutions. And there'll be plenty of instances where you can't do a u substitution like we did up here. So you have to solve this the more challenging trig substitution way, like we did in red, and then blue, and then green, and then purple. It's a lot, it's hard, but hopefully when you were watching this method, you saw a lot of parallels between the other problem that we did. We did a very similar trig substitution, which left us with a very similar expression underneath the radical, where we used the Pythagorean identity to change 1 minus sine squared into cosine squared and cancel out the radical. That left us with an integral involving some trig functions. We needed to integrate that. The method of integration was pretty different because we had a different expression, but in both instances, we were integrating some trig expression with our variable being theta. Here we used the Pythagorean identity. Down here, we used a u substitution. But one way or another, it left us with an expression that didn't have any integral symbols in it anymore. So a really nice expression. Negative 125 over 3 cosine cubed theta plus c in this example. At this point, the finish line is kind of in sight. The goal of these problems is to integrate, and there's no integral symbol left, so you're done integrating. However, this isn't a good final answer because we need to switch our variables back from thetas to x's and simplify the inverse trig function that was nested inside of the trig function. In this case, it was the cosine of the arcsine of x over 5 that we had to simplify with this triangle method. In this case, it was the cotangent of the arcsine of x over 3 that we had to simplify with this triangle method. But the steps we used in pink and purple here were very similar to the steps that we used in green down here. After that simplification, we had our final answer and we were done. If you're following all this really closely, right now you might be like, okay, I think I have most of the pieces. I think I have most of the steps. The one thing that you keep doing and not really explaining why you're doing it is your original trig substitution. How do you know that theta should be equal to the arcsine of x over 5? Where did that come from? I mean, yeah, it makes things work out really nicely so we can use our Pythagorean identity there, but how do you know that that specific trig substitution is what you'll use to make this work out really nicely? Is it always going to be the arcsine of x over some number, or are there ever instances where you use something different as your trig substitution? Well, it turns out that there's 3 different options for your trig substitution. We've only seen one of them so far, so I'm going to have to do at least 2 more videos. But all 3 options are fairly similar. When you're doing a trig substitution, you're doing it because you have a radical with multiple terms underneath the radical. And I can even be more specific than that. Either you'll have a number minus x squared under the radical, or you'll have a number plus x squared under the radical, or you'll have x squared minus a number under the radical. Those are the only 3 options that you're going to do trig substitutions for. So when you see a problem and part of the integrand is any of these 3 expressions, it's a good idea to think about trig substitutions. It's worth pointing out that just because one of those 3 things is part of the expression, you don't necessarily have to do a trig substitution. Like we saw in this example, there's a much easier way to get this answer. But if you don't see an easier way, or you don't want to think about looking for an easier way, recognize one of these 3 forms, think trig substitution. If it's this first one where we have a number minus x squared under the radical, what every book I've ever seen will tell you is that the trig substitution that you should do would be x equals the square root of that number times sine of theta. I'd argue that technically the substitution that you're doing is theta is equal to the arcsine of x over the square root of that number. But hopefully we've hammered this enough where you see that these 2 things really represent the exact same equation. And maybe it's easier to think about it this way, but then immediately solve the equation for x when you're trying to figure out d theta. In the 2 examples that we've seen so far in these videos, one integrand contained the square root of 25 minus x squared, and the other integrand contained the square root of 9 minus x squared. So they both fit this form where we had a number minus x squared. When you're doing your substitution, what you have to do is figure out what is the square root of that number. So in this example, the 25 is the a squared, and therefore the a is equal to the 5. So when I see the square root of 25 minus x squared, I know x is equal to 5 sine of theta. Over here, the value of a squared is equal to 9. Unfortunately, my 9 kind of looks like an a, but this is not an a, it's a 9. So if a squared is equal to 9, then a must be equal to 3. So my substitution over here would be x equals 3 sine of theta. Or another way to think about it is theta is equal to the arc sine of x over 3. But what if you're working on a problem and you see a radical with multiple terms under it and it's not a number minus x squared? What if it's a number plus x squared? Well, good news, there's still a trig substitution that works. It's just you don't use the trig function sine, you use the trig function tangent. Everything else works out the same. So if, for example, you had the square root of, 100 plus x squared, that would mean a squared is equal to 100, therefore a is equal to 10, and the trig substitution I want to do is x equals 10 times the tangent of theta. And then finally, if you don't have a number minus x squared, but instead you have x squared minus a number, so x squared minus 6, sure. Then you'd recognize you're not in this form where the trig function uses sine, you're in this form where the trig function uses secant. We got x squared minus a squared, so playing the role of a squared is the number 6, and therefore playing the role of a is the square root of 6, so x would be equal to the square root of 6 times secant of theta. There's only 3 different types of trig substitutions you're going to do, and they're summarized in parts A, B, and C here. Is it reasonable to ask students to memorize all this? I don't know. While I'm making this video, I'm kind of leaning towards, nah, it's probably not. I hate to make statements like this in videos because hopefully I'll be using this same video in 5 years, and maybe in 5 years I'll change the way I write tests and stuff. But knowing me the way I know me, if I gave you a question that had something like this in it and I wanted you to use a trig substitution, I'd probably say something like hint. The appropriate trig substitution comes in the form of x equals a times secant of theta or something like that. But confirm that in class. I probably shouldn't have said anything at all. If you can do the proper trig substitution, you've started this problem out on the right track, and hopefully you'll be able to recognize the commonalities to complete parts 1, 2, and 3. Part 1 will always be to get rid of the square root. Note that we have a square root here, here, and here. And in order to get rid of this square root, you have to change 2 terms into 1 term, and to change the 2 terms into 1 term, you're going to be using the Pythagorean identity. After you've gotten rid of that square root, you're going to be left with an expression, a trig expression that doesn't have that square root anymore, so you're going to be able to integrate. Really, this second part is where the difficulty level of these trig substitutions varies, because the way you integrate is going to depend on what you're left with. It's going to depend on the rest of the expression after you get rid of the square root sign. But it shouldn't use any new techniques. It should only use the techniques that you've learned so far in this class. After you integrate, you'll be left with an answer without an integral symbol with the variable theta, which is great. You're kind of done with the calculus part of the problem, but you're not done with the problem because you shouldn't leave thetas in your answer, because the question will be written in terms of x's. So part 3, you need to change your variables back. And typically when you do that, you'll be left with an inverse trig function nested inside of a trig function, which is something you're going to want to simplify. I think what you'll see is part 1 and part 3 are always fairly similar. It's part 2 where these problems differ. And maybe part 2 feels harder than it actually is because it's hidden inside part 1 and part 3 and it's so easy to get overwhelmed, which is why I think it really helps to think about it in terms of these different steps. You have this big process in front of you and kind of a blueprint for how to accomplish that process, but that blueprint involves lots of different steps, and you'll need lots of tools to accomplish those different steps. Many of those tools will be related to stuff that you learned in a trig class. What I tried to do here is write all the stuff that you'll have to remember out of a trig class. The Pythagorean identity and its variance. So here I'm talking about sine squared theta plus cosine squared theta equals 1. And then variance of this equation like 1 minus sine squared theta equals cosine squared theta, for example. Or tangent squared theta plus 1 is equal to secant squared theta if I divide all 3 of these guys by cosine squared. You can also divide all 3 of these guys by sine squared to get 1 plus cotangent squared equals cosecant squared. I'm able to go between these different variants because I'm really comfortable changing between the 6 different trig functions. Recall that all 6 of the trig functions can be written in terms of sines and cosines. Sine's already just equal to sine, cosine's equal to cosine, tangent is sine over cosine, cosecant's 1 over sine, secant's 1 over cosine, and cotangent is cosine over sine. I won't bother copying those because I have them earlier on in these notes. Finally, the kind of icing on the cake at the very end, where you already have the right answer and the right variable, but really you should simplify your answer, is this step where you have nested trig and inverse trig functions, specifically an inverse trig function nested inside of a trig function. And the way you simplify that is this method that we showed in green here, which may feel new to you if you didn't learn this in a trig class, but the good news is you're going to be doing this in every single one of these problems. So in the next couple videos, where I show you examples of this type of trig substitution and this type of trig substitution, you'll get lots of practice on this fourth and final step. I know it's overwhelming and I know how hard this stuff is, but keep reminding yourself that they're very predictable. Rewrite one of these examples that we've already done in these notes really carefully and really slowly so that it makes a ton of sense to you. And then when you get a new problem, do it side by side with that problem handy. And that should really help you understand the new problem. Hopefully anyways. I'll save future examples for the next video.